étudiant qui était là, qui est parti.
C'est venu, peut-être, il y a quelqu'un ici, non?
Oui, il va arriver.
Il va venir, il va revenir. J'ai beaucoup aimé ce bouquin.
Il parle bien. Oui, il est bien. Oui.
Pas mal de
Il y a pas mal de choses. Et il n'est pas facile à trouver.
Ah, ici, on va.
So, yesterday we had an experimental and theoretical explanation of the anomalous magnetic problems, situations. And today we will start computations. And I want to do again the one loop calculation that triggered it, because it's nice at least to have done it once. Do you already know it?
One loop?
Yes. You did it?
We have done it.
Okay.
The one loop calculation.
Okay, do you know?
With final tricks. Using final tricks.
Yes, okay. Let's start. So I said that in quantum electro dynamics at one loop, the contribution to the anomalous magnetic moment comes from this diagram. Of course, the diagram contains more, because we saw that there is also a contribution from the Dirac form factor. And so, if you write the Feynman rules like this, conventions, you have following thing. So the first thing to do is to try to see if the diagram is diverging. Okay. So we compute the superficial degree of divergence, which is given by this formula. For L minus E by external minus external bosons. Okay? Here we have only one for external boson and two external fermions. So we find 0, which means that this logarithmically divided diagram. Okay? So in principle, you should take a regulator to compute the Feynman integral. But here we know that in fact, I will not do it to simplify again the calculation, because we compute the anomalous magnetic moment, which is, as we will see, not diverging. All the divergences, infrared and ultraviolet, are in the F1 form factor. Okay, so I will stay in 4 dimensions, not use the dimensional linearization for this simple calculation. Okay? But the steps usually contain this kind of quantum theory integral. So you begin by computing T, then you write the Feynman rules. Okay. I will write. So I stay in 4 dimensions. Okay, you begin by this. You find the vertex. Then you have the propagator. Okay, then another vertex. Another vertex. Here, new. Another propagator. This one. Then the last vertex. Okay, there is a minus I that is in fact here because it's not real for the side. That is the propagator of the photon, which contracts between this and this one. Where you can put a mass, but here it's not necessary for G minus 2. So we put it to 0. And you have also the gauge part. Like this formula, and we will see also that the gauge part does not contribute to F2. Therefore, we will be able to choose K equal 1 the finite gauge. So the first thing to do to complete this kind of integrals, the finite parameterization. Which is given by the following formula. Okay, 1 over A1 to AN to the power alpha 1 alpha n, where alpha e are C numbers, is given by this formula. The products here of the different gammas and the integrals of your finite parameters. The delta function. And here the integrals divided by this to the power sigma alpha g equal 1 L. Okay, so this is the first thing to do. Then you perform the change of variable. Okay, if you are in d dimensions, d otherwise work like this here. Then you have to do the archaeology, which means to compute the numerator. It's not so easy when you go deeper in the extraction, of course. These steps may be inverted if you want, depending on the choice. Then you have the symmetric integration to perform. Okay, for instance, you use these formulas gamma n minus 2 over gamma n to the power n minus 2. And other tricks, like, for instance, if you have an odd number of power of k in the numerator, this kind of integrals are 0. Okay? So you know this already. Then, yes, I did not write the E epsilon construction here, but it is understood. Okay? And here, when you compute these integrals, they are converging. You can do the deep rotation to avoid the epsilon description. This is allowed since the integrals are converged, your integrals are not. Then you should go to dimensional regularization to avoid the E epsilon by deep rotation. And then, last but not least, you have to compute the finite parameter integrals. Which may be very non-trivial. Then you have the rest. And let's go for normalization after, if you need. If you use diverging integrals, of course, not necessary. Okay, so let's apply this integral what we said. I just say that we will put lambda equal to 0, since there are no infinite divergences in F2. I know it. Check it by computing the integrals at the end. Then we will take a equal to 1. So it will simplify a bit. We will find well, this is sandwiched between the spin-offs, of course. And you find, yes, gamma mu divided by 2 prime k equal to minus mass square times e plus q. Okay. So I said that you have to do the Feynman parameterization, which means here 1 over a, b, c equals integral over x and integral over y 1 over a minus b times x y plus b minus c and x plus c to the power 3. Okay, then after you choose with A, B, C. Okay, here what I chose was A, B, and C. Okay. So, if I choose this, I find we get to do the exercise A minus P equal to 2 prime minus P times Q minus P times Q. Let's see, of course, the square. So that 1 over my things here is equal to integral over what is x divided over y 1 over k plus I x plus x1 q minus r squared to the power of 3, where r squared is simply why it is so simple, because the anomaly is stated at q squared equal to 0. So in all my calculation, when I find q squared, I put it to 0. But otherwise, there is a q squared equal to 0. Okay? I put it to 0. Therefore, the change of variables will be here. Okay? Change of variable A plus x plus x1. Okay. Now we have, we know what to perform here in the generator. And but before, if you want, you can compute the trace without the change of variable. It's the trace, it's not the trace. So for instance, if I put 1, 2, 3, 4, 5, 6. I have 9 terms to compute. And let's do the example of the first one. So minus, so 1, 4, which is gamma mu slash prime, gamma mu slash gamma mu. This is, in fact, equal to minus 2. Invert the P and P prime. P prime gamma mu P. Okay? There are formulas that you have to know, of course, for contracting, the gammas, the gammas, and you can easily demonstrate this. You can also know it by heart. Then, with this, we see that we can, yes, we should sandwich here. Yes, I forgot to switch. between u bar p prime and u of a. So you can apply the Dirac equation and you get, well, you cannot directly apply because this has to apply on the left and this on the right, so you have to turn. So you use the uniform algebra of the gamma matrices. You invert this, you obtain minus 4 slash prime mu plus 2 slash prime slash gamma mu. Okay? This can apply the Dirac equation is minus 4 m prime mu. Okay? And this will apply again the uniform algebra and get this minus 4 m prime mu plus 4 slash prime slash yes. Okay. Yes, minus 2 p dot p prime. Sorry. If I did not make a mistake, so this is minus m slash m, and this p dot p prime is related to p prime minus p squared, which is q squared, and since the p squared is equal to m squared and p prime squared equal to m squared, because they are on the match chain, so you can simplify this by using this relation. You get simply m squared minus q squared over p. Yes. Then this has to be exchanged once more. Minus 4n by mu plus 4m squared minus q squared over 2 times gamma nu plus this that will change, so minus 4m squared gamma nu because p slash by the Dirac equation which is the mass. And then the last one plus 2 and p mu. Is correct. I'm not sure it's correct. This is always the problem when you do the calculation on the blackboard. Okay, so this is correct. This is, yes, I already know it. Do you see something wrong? They inverted in fact. Minus plus 2m squared gamma nu. Yes, seems to be correct. So on this term there is no change on variable, of course, because there is no k dependence. Let's compute another term, just one, a simple one. Let's see what we have to do when we have to change in our term. It's clear anyway. So let's compute, for instance, 2, 6. There are only two gammas here, so this gives simply 4m k u. In fact, this time the dimension which is 4, and we get the m before. Okay, so in the C2V we get 4m u minus x minus q u xy. Okay, so exercise we compute the other terms. So even if it's a simple calculation, you see that you easily make some mistakes. Easy way to check. Really each step carefully. At the end of the calculation, you will have to reorganize things in order to separate the contribution from F1 to the contribution from F2. This may be done with the use of the coordinate identity. Just recall that we have this. To obtain this, it's not easy in fact from the end when you sum everything. There is another way that you're then using the coordinate identity, you have the coordinate identity if you want. This is done in some books. What?
No, I'm joking them. They are PhDs in this subject. They have here work a lot of a full variety of coordinate identities in many situations. So this is why they are laughing. Now they are doing coordinate identity, not ADS space, you see.
Okay. So God used convex. So, but in this case, in this simple case, it will work without too much job, but it's easier, in fact, to use some projectors to get directly the contribution of each form factor. And you can, in fact, show that the Fi, F1 and F2 are given by the following formula. n. Okay? Where the lambda in the 2 case is given by this equation. Times 1 over 2 square minus 4n square from mu minus n over 2 square, and I don't do by 2 square plus 2n square divided by 2 square minus 4n square to the power 2 mu plus 1v. Okay, so with this, it is in fact easier than to try to reorganize the numerator. Just apply this formula on what you get. And so let's see what it is when, for instance, you have the contributions, which is PU. Just as an example, you have also other cases to conclude that this will give the trace on gas on the gamma roots. So if I write it as like this, A times gamma mu plus B times mu plus B by mu. Everybody writing everything. I have that the action of lambda over mu is the trace of lambda 2, so A gamma plus slash mu slash prime plus n. Okay, so once more, it's nice to put numbers above 1, 2, 3, 4, 5, 6. There are 8 terms, and you can compute them just like, for instance, 1, 3, 5 equal 8 trace gamma slash 5 slash, which is
What number?
yes, 0. 0, because we have an odd number of gammas. Okay. Well, you can do the others, of course. One. Well, you know that. Okay, so we can find at the end. For A and the prime plus 4a. This is the exercise. Plus 4b prime times square plus prime plus 4b. Yes. Okay. And if you put here p prime for n squared minus 2 squared root 2, you find at the end minus n. So the action of lambda over PU is simply minus n. Okay? You can do similar calculations to show that on the other variables of your problem. You have trace of that over gamma n equal. So what? Number 2 equals 0 because okay, this is the contribution to F1. We have gamma nu times gamma nu. Gamma nu, remember the decomposition of the matrix element. We have this equation also, Q nu equals 0. And others, if you want, they are not, you don't have to derive them, but you can simplify the calculation. For instance, this one, minus 2m, etc., etc. You can do a formula that you use if you have several calculations to do the same with the same mathematical compute. Okay. So using now the change of variable, we use it. We can now do the symmetrical integration. Get at the end, I will write the formula. 1/4 gives 4m squared plus 4m squared. Okay. 1/5. So these are not those 1, 2, etc. These are from the other before. Just like let me here if you want to redo the calculation by yourself. Plus 4m squared xy minus 4m squared x 1/6. This is minus 4 squared. 1 7 does not exist. 4. This is minus 4 squared x minus 4 squared this way. 2.5 is the 4 squared x squared. 2.626 4m squared x 7 no 3 4 minus 4m squared and 3 5 is 4m squared x. The other do not give anything, so you can sum these contributions. And you get, finally, for the numerator, you get 4m squared x squared minus 4m squared x. You sum everything. So, now you see the fact that you have this little a squared minus f squared power 2. So this is, in fact, this is f squared. This is equal to I to the power of 1 minus 6. Gamma m squared power minus 1 over 3 equal to minus 9 over 32 pi squared 1 over m squared x squared. I recall that m squared m squared. Okay. So you insert this equation with the numerator in the parametric Feynman integral that you get from the beginning. And you get again this. You have an integral over y with no dependence on y. So only one. This and it's minus 1. So this comes from here. Divided by x squared, which is not moved. Square integral of 1 over x minus 1 equal square over 4 pi. The Schwinger result we obtained in 1948. calculations that we have time to do. Because I recall you that, in fact, the two calculations of the partners community moment involve 7 diagrams that I can go now. So you have this, you have this, this one, plus the symmetrical diagram, this one, plus symmetrical, and the last one, which is the one that one can do, in fact. This is what I propose to do is compute this, but with L and N prime. Two different vectors. Okay? Because this took 10 years to be computed historically. So I think let's do it now. And this is really more simple. Okay. So for this, you see that it is the same value for D. Okay, this is D equal to 0. This is diverging also. But you have a sub-diagram inside, vacuum polarization, that is also diverging. But what we want to do is to compute it first, and then, because it will diverge, normalize it, and then put it inside, because we know that at the end, the rest of the diagram will not diverge concerning the contribution to F2. Have you already done also this calculation of the vacuum polarization?
Just one loop.
Yes.
Polarization at one loop, yes. They did yes. But not this two loop graph they have not.
Yes. Okay. So we begin by the inside subdiagram, which has D equal to 4L minus 3. Okay, so in this case, what is this? No. This is the good answer, in fact, that you should not from this zero.
Yeah, but this is not more identity.
This is 0. Okay, you have no external terms. You have 2.
I was looking at the big diagram, two-loop diagram.
Ah, okay. No.
Two-loop
Sorry.
diagram.
I'm sorry, I forgot. Yeah, the two is 0. This also is 0, in fact. This is the effective degree of divergence is 0, but we can't see from this formula. Okay, so this has to be computed in dimensional regularization. Okay? But before I will put here the conventions. So this is L prime. The momentum is like this. You have K. Here. This is P plus K as before. And then Yes. Right. So, yeah, L, K, L plus K. Okay. So, you have this loop, being written as I polarization. You have the minus one because of the Feynman rules. Now we do it in d dimensions. You have minus from here. We go like this. So you have gamma sigma. I write here the Dirac indices. A over k squared plus k squared minus the mass, which is not the same as before, as I told you. I don't take the same reluctance inside and outside. Then we have here minus gamma rho. This is, yes, correct. Times k square minus n dA. Now because there is a loop, okay, so the arc indices are compacting together to give a trace. Okay, so this is equal to minus I forgot to put this in order to have no dimensions, no massive dimensions in the dimension framework. This is trace of gamma sigma k slash plus x slash plus n over k plus n squared minus n squared gamma tau k slash plus n like k squared, but no, it's not k, like okay? So the Feynman parameterization is even simpler in this case because you have only two things. So it is minus and we take a equal to k plus square minus n square and b equal the other, so x square minus n square, we get 1 over my things equal to 1 over it's 1 over n plus k x square minus n square plus m squared. So the change of variable will be the following. And this is theta minus x. Okay? So we do the trace. So we already did it. An example of trace calculation, so we won't do it again repeatedly. So we have compute, in fact, yes, it's not anymore, but if I do a change of variable, we have to compute the following trace. Plus m gamma tau okay. And if you do that, taking into account symmetrical integration, that will allow to keep all the terms L theta. Okay? You find at the end four minus epsilon. We do it in t dimensions. Okay? Of course. Times 2 n tau L sigma minus L squared. J sigma tau minus x times 1 minus x times j minus epsilon k sigma k tau minus k sigma tau k squared plus 4 minus epsilon times m squared is not hard. Okay, this is what you find at the end. But in fact, in this equation, you can find the appearance of this, which will allow to simplify a bit. Okay? You can write this, so this is that side. So you can write it as 4 minus epsilon times 2 x squared j sigma tau 4 minus epsilon minus x squared. And this times k sigma k tau minus j sigma tau k squared plus the convolution from r squared. So if I call this b, I call this a. If you compute the integrals between these two things, you will find at the end, if I do it, the sum is 0. not here, but by using the integral over momentum. It gives 0. Once the integrals are completed. So you saw that, no? Yes. So what does it mean? This means that at the end there is only this contribution. Okay? So at the end we have pi sigma tau, which is equal to minus power 1 x is 1 minus x 4 minus x squared sigma tau square times can be written as minus square times k sigma k tau minus sigma tau k square times 4 minus square I gamma epsilon over 2 divided by 16 pi square 1 minus x to 4 epsilon then x 1 minus x square power minus epsilon of this by using the formula, well-known formula for this case. Okay, so is there a problem here? There is no problem, but where is the divergence? Yes,
And this one property.
yes.
The function.
Okay, the gamma function as poles at all negative integers of 0. So this means that gamma epsilon will diverge when epsilon goes to 0. If I gamma x that 1 over x gamma that 1 plus x I can develop. That's the epsilon expansion of the gamma function. This is 1 over x times gamma 1 plus the derivative of this. This is gamma prime times x plus gamma k taken in 0 times p squared log 2 plus etc. Okay? So this in fact is gamma 1 plus x times psi 1 plus x squared psi is the polygamma function, digamma function, polygamma of order 0, taken is equal to 0. So this gives C1, which is minus gamma Euler. Okay. If I replace x by epsilon log 2, this is 2 over epsilon times 1 plus epsilon over 2 times minus gamma Euler plus order epsilon squared. Okay, it's enough. In principle, some calculation you should go beyond this level by computing these terms here. And you do the same for this, and this, and you perform the expansion. At the end, you find this. Sorry. You find equal. Times the function of p squared, which is written as alpha over pi 1 x times 1 minus x times 2 over epsilon minus gamma minus log, because when you expand this, okay, this is exponential of minus epsilon of 2 times log of r squared. So there is a log that comes. The log is given as m squared minus p squared x times 1 minus x divided by 2 pi mu squared. And these terms come from this one of pi when you expand epsilon, and this one we add in the beginning to avoid that the logarithm has dimension of mass. It's massive dimension. Plus epsilon. On this. Okay, so here, clearly, the energies is here, and we have to normalize it. So, we bring on the mass shell, which means that we take r of k squared equal to k squared minus pi 0 go. This mathematical stream we get at the end this formula minus 2 alpha I equal to 1 x times 1 minus x logarithm of 1 minus a square over n square x times 1 over 1 minus x. Okay, so this is the normalized vacuum polarization in quantum dynamics at the now you have to insert it inside the vertex function. So this term here, when we invert it, put it inside the vertex function, we need 0 in fact. We replace in the one loop calculation the photon propagator by this expression. Okay, this is what we have there. I changed the sign. Okay. Yes. This is the replacement of this propagator by this one. Okay, so that we will be able to use the one-loop calculation that we did after a few other calculations. So it's why this is why it can become easy. I mean, in a few hours. Instead of 10 years for the others. Okay, so if you compute this, you find this. Times r. Okay. And now you insert it, in fact, in the one calculation. So you have this. Integral compute. Same as we did a few minutes ago, which is also the reason why I wanted to do it. But now a bit motivated. By this function. Times j mu over k square minus k mu k over k square times R K squared. So it is easy to show that this term will be 0. So do you see why? Well, if you did not the calculation once, it's hard to know, and even if it's very easy. But because in fact, when you contract K with the gamma, here, you have K slash here, K slash here. Now K slash, you can write it as K slash minus T prime slash plus N. And here also, this is the prime plus. Okay. And here also, we write it as K slash plus K slash minus N minus K slash plus N. So we have a cancellation between the numerator and the denominator. And also, what will stay at the end is something that by the Dirac equation, no, it's not 0. Is the mass, because it will apply on this pure here and here, and it will at the end give something which is proportional to gamma nu. So 0 for F2, but not for F1. And this is also the reason why F1 is gauge dependent at all loop, because it's the same. We have see the same pressure that we would have in the free propagator if we keep non-Feynman gauge in the beginning of the volume calculation we did through parallel. Okay? So at the end, this will give 0 to for F2. So now this we contract with this, and we are left with this. Okay. For F2. But so now what we should do is to take this and put it here. Here and compute. So this will not be obvious like this.